All right, the last section we had in Chapter 3 is differentials. In the previous section, we studied something called Newton's method. What was Newton's method all about? The close approximation to what? Okay, so Newton's method, this was a technique for approximating solutions to equations. And how did we do that roughly? We had a formula, and the formula involved, the right answer is always derivative. The formula involved a derivative. What we did in particular is we approximated the curve by the tangent line, and we solved the tangent line. This used the tangent line. Differentials is similar. Differentials, this is a technique for approximating values of functions. And again, it's going to use the derivative in the tangent line. To do this, we will use the tangent line. All right, and here's the basic idea. You've got some function. This is our function f of x. And I'm going to pick 2 points on this function. There's 1 point right there. That's x1 comma f of x1. And this is x2 comma f at x2. And generally what's going to happen is f at x1 is going to be a value we can evaluate easily. And f of x2 is one that we can't evaluate so easily. And we'll see what I mean by that in just a minute here. All right, so we have a lot of notation in this section. Here's x1, and here's x2. So the first symbol we have is the difference in the x values, x2 minus x1. What do you think we should call x2 minus x1? Delta x is the common symbol that's used for x2 minus x1. And then we have these two values up here, f at x2 and f at x1. And we also subtract them, f at x2 minus f at x1. And what should we call those? Delta y. That's the change in the y value, isn't it? Delta y. So, in words, delta x is the exact change in x. And delta y is the exact change in y. Well, then what we're going to do is we're going to draw the tangent line at x1. So the tangent line at x1 would look something like that. So it still has this point, x1 comma f at x1, but at x2, it has a different y value. What should we call that y value? I'm just going to call it y2, I guess, would be a good number. And in just a minute here, we'll figure out what that y2 value really should be. Now, I want you to notice one thing. Is y2 exactly equal to f at x2? No. Is the y2 value close to the f at x2 value? Somewhat close, right? when will the y2 value and the f at x2 value be fairly close to each other? Well, this one's a curve, and that one's a line, so they're definitely not going to have the same slope. At this given point, they'll certainly be good. What if I picked my x2 to be closer to my x1? Would my y2 and my f at x2 be closer to each other?
Yes.
Yeah. What if I had picked my x2 to be way out here somewhere? Would my y2 and my f at x2 be very close to each other? No. So what do we want to have happen? We want x2 and x1 to be close to each other. So if delta x is small, and we're not going to define exactly what small means, but if delta x is small, y2 and f at x2 will be close. And that's what we want. The whole point behind this is that this f of x2 value is one that's difficult to figure out. But this y2 value is going to be one that's going to be pretty easy to figure out. We'll figure it out from using the equation of the tangent line. All right, well, let's figure that out. What would the equation of the tangent line be? How do we find the equation of the tangent line? I take the derivative. So the slope is going to be f prime at x1. So our tangent line would be y minus the y value. The y value is f at x1 equals our slope, f prime at x1 times x minus x1. Okay, so now, how would I find the y2 number? I would plug x2 into the green formula, right? I would plug y2 in there. So to find y2, I would have y minus f at x1 equals f prime at x1 times, I would plug in x1, or x2, I mean, x2 minus x1. What's x2 minus x1? It's delta x. I'm also going to call it, we're going to use another symbol, dx. Oops. Equals x2 minus x1, which happens to exactly equal delta x. Why dx instead of delta x? It's looking like derivative. That's exactly right. On the left-hand side, what's this y minus f at x1? Well, in a picture, it would be this distance, wouldn't it? Because this y is really the y2 number. Oops, now you can't see the picture. There we go. This y is really the y2 value that we're looking for. And f at x1, that's that same y value right there. So that's y minus f at x1. What should we call that? Well, delta y was this distance. This distance was delta y. So I want to use a different symbol for this distance up over here. It's going to look a lot like this symbol. dy. That's the change in y, so we're going to call that dy. So we have dy is f prime at x1 dx. And this formula, this is called the differential. What's important about this formula is that dy is approximately equal to delta y. They're not exactly equal, but they're close. And that's going to help us to approximate values. And you'll see here how here in just a second.
Sorry, what was the dx again?
Dx was x2 minus x1. Dx and delta x happen to be exactly equal. Dx and delta x are exactly equal. Dy and delta y are approximately equal. They're close to each other. All right, so here's the idea behind this. Approximate the square root of 81.1. It's approximately 9. Why do you say it's approximately 9? All right, so I know that the square root of 81 is 9. So in all that stuff we were just doing a minute ago, x1 is the number 81. x1 is usually a number that you can plug into your formula and get a very easy answer. In this case, I can plug in 81. What's my x2 number? Not 0.1. 81.1. x2 is the value that I want to evaluate. I want to be able to plug in 81.1, but I can't plug in 81.1 into that square root function easily. Okay. So what's delta x? Well, it's the same as dx. It's 0.1. It's 81.1 minus 81. It's 0.1. All right, now I want to find the change in y. So dy is f prime of x dx. In this case, what's my function? What's f of x? I don't really have a function written down here, but what should it be? It should be square root. We're trying to approximate the square root of something. So f of x is square root of x. So dy is, what's the derivative of square root of x? 1/2 x to the negative 1/2 times dx. Now I'm going to plug in my numbers. What number am I going to plug in for x? Which number is the easy one to plug in? 81 is the easy one to plug in. And what's dx? That's 0.1, isn't it? dx and delta x are exactly the same thing. So dy is 1/2 times 81 to the negative 1/2 times 0.1. That's 1/2 times, what's 81 to the negative 1/2? 1 over 9. Why 1 over 9?
Because it's 1 over the square root of 81.
The negative power drops it to the bottom. The 1/2 power is the square root, so that's 1/9 times 1/10. Instead of writing it as 0.1, I'm going to write it as a fraction. What's 1/2 times 1/9 times 1/10? 1 over 180? All right, so here's my final answer. The square root of 81.1, you told me it's about 9, which I believe. How far off from 9 is it, approximately? About 1 over 180. All right, so just for fun, give me a decimal approximation for that. What's 9 plus 1 over 180? You brought a calculator today. I didn't bring one. 9.0056. And what's your calculator say for the square root of 81.1? So, is our approximation for the square root of 81.1 pretty good?
Mm-hmm.
Yeah, it's accurate to 3 decimal places. Almost 4. Not bad. Questions on that? All right, give me another value you want to approximate. Anybody have a good idea? Something you want to approximate? Approximate the square root of 2.
Does it have to be square root?
No? Let's make it cube root of 2 then. Doesn't have to be square root, it could be cube root. Approximate the cube root of 2. All right, so in this case, what's our function going to be? Cube root of x. And then I need my x1 number and my x2 number. Well, x2 is 2. I already know that one. I need a number close to 2 that I can plug in to that function and get an answer pretty easily. 1. I can plug 1 into that function. Can I? Cube root of 1 is 1. So this time our delta x, which is exactly equal to our dx, is 1. Okay. Then I need to find dy. dy is equal to f prime of x dx. What's f prime of x this time? 1/3 x to the negative 2/3 times dx. So dy is 1/3 times 1 to the negative 2/3 times 1. Now notice these are two different ones. The 1 to the negative 2/3, that's because I plugged in the x1 number. And the dx was 1 because we computed dx to be 1. So I used the number 1 twice, but that's just a coincidence. All right, so that's 1/3. So our answer this time, the cube root of 2, is approximately how much? 1 plus 1/3, which is 1.3 repeating forever. And again, just out of curiosity, type in cube root of 2 into your calculator. Say that again, please. 1.25992105. Close enough. 1.25995. How good is our answer this time? Not as good, is it? 1.3, 1.3. It's only good to 1 decimal place. How come our answer this time isn't as accurate as our answer was last time? In this, yeah, you got the right idea. In this case, for the first example, our delta x was 0.1, where for this example, our delta x was 1. The smaller the delta x value, the better the approximation. Still not too bad, though, if you think about it. It's still good to one decimal place as an approximation. Questions on that?
Now, what if it was like a parabola or something like that?
What if it was what?
Like a parabola like that,
Like a parabola? Okay.
that's what I was asking before. Like, probably going to be square root 4 or something.
No. So you're saying, what if we had f of x equals, you said a parabola, so we'll have 3x squared plus 2x minus 8. And I wanted to evaluate f at 1.99. Could I plug in 1.99 and work it out? I could. I could even do it without a calculator, couldn't I? I mean, it'd be kind of a pain in the neck. I don't really want to take 1.99 times 1.99 and work that out by hand, but I could if I really had to. What's a number close to 1.99 that I could plug in easily? 2. All right, so I could plug in 2, and I could do that pretty easily. That's 3 times 4 plus 4 minus 8. That's 8, correct? So f at 1.99, that's going to be close to 8. The question is, how close? All right, so I need to know my delta x, which is my dx, and then I need to find my dy, which is f prime at x dx. In this case, what's dx? 0.01? Close. Negative 0.01. Why negative 0.01? Right, you got to remember which number is your x2 and which number is your x1. Your x2 is the value you're trying to figure out. The x1 is the one that's close by that you can easily plug in. So in this case, x2 minus x1 is 1.99 minus 2. So your dx value can be negative. In this case, it's negative 0.01. Okay, so what's dy? dy is f prime of x. What's f prime of x? 6x plus 2 times dx. All right, so dy is, I now take my value and I plug it in. What number am I plugging in for x here? Not 1.99. The easy value. X is the number 2. We plug in the easy value for x. So that's going to be 12. I'll write it down. 6 times 2 plus 2. And what's dx? Negative 0.01. 6 times 2 is 12. 12 plus 2 is 14. What's 14 times negative 0.01? Negative 0.14. So f at 1.99 is approximately 8 minus 0.14, which is 7.86. And again, just out of curiosity, when you grab your calculator and you exactly plug in 1.99, plug it in up here, what do you get? $7.8603. So again, how good was our approximation? Pretty good. Good to how many decimal places? Good to 3 decimal places. Just tack a 0 on the end up there. Questions on that? All right, well, the big obvious question is, why? I have my calculator. If I want to estimate the square root of 81.1, I grab my calculator, I type it in real quick. It gives me a very accurate answer to about 8 decimal places. Why do we bother with differentials?
You don't have a calculator.
Okay, how often do you not have a calculator?
Rare.
That's not really a very good answer, is it?
Did you have to prove something? Maybe?
Maybe. Probably not. All right, well, this section, in my opinion, always comes in a bad place. This section always comes in Chapter 3 of every book I've ever seen. Well, maybe not Chapter 3, but it comes with all the stuff dealing with derivatives. This section really should be in Calc 2. And it really should be right before something called Taylor polynomials. This is called, the approximation that we're doing, this is called the first order approximation, also called the linear approximation. When you take Calc 2, you're going to learn to do polynomial approximations. And so what happens is, you can, in Calc 2, using second derivative, third derivative, fourth derivative, so on and so forth, we can show that sine of x is approximately equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial. And you can keep going as long as you want. Sine has all these odd powers divided by these odd factorials. So this would be called the 9th order approximation. And in order to get it, I would have to use the 9th derivative. So something to look forward to in Calc 2. We'll be doing 9th derivatives. Good times, huh? Well, who cares? What's that all about? Well, when you pick up your calculator and you type in sine of pi over 7, how did your calculator get that answer? Does it have a big table of trig values stored in it somewhere? No, it doesn't. What your calculator has stored is it has an approximation formula stored in it. And again, I'm going to be honest with you, I'm pretty sure that's probably not the formula that's stored in your calculator. Again, this was developed by a couple guys named Taylor and Maclarian, who lived several hundred years ago. Since then, there have been faster algorithms developed, but they all are based on this technique. So this is really a build-up to how technology works today. That's why we study linear approximation, and that's why we study in Calc 2, we'll study polynomial approximations. Okay? So all those unusual functions in your calculator, sine, cosine, tangent, logs, e to the x, those all have some sort of polynomial expansion that they're using to give you those values. Questions about that? All right, so here's the other thing we're going to use it for. Something where it is still used. For example, number 26. The measurement of the radius of a circle is 16 inches with a possible error of 1/4 inch. And it asks you to use differentials to approximate the possible propagated error in computing the area of the circle. And then part B, approximate the percent error in computing the area of the circle. All right, so we've got, it told us we're building a circle. Radius is 16 inches plus or minus 1/4 of an inch. So again, if you ever go into machining, if you ever go into building items, you'll find that you can't make a circle of exactly 16 inches. The equipment you have just isn't that accurate. It'll be 16 inches plus or minus some amount. No, actually a quarter inch is pretty big if you're machining. With machining, you can usually get down to hundredths of an inch, but let's play with quarter of an inch for a while. So what it wants to know is, if the radius could be 16 inches, but it could possibly be a quarter inch too big or possibly a quarter inch too small, how does it affect the area of the circle that you're making? How far off is the area? Well, how do you find the area of a circle? Pi r squared. So the area should be pi times 16 squared. What's 16 squared? 256. So assuming you could cut your radius at exactly 16 inches, the area of your circle should be 256 pi square inches. But we can't cut it exactly 16 inches. Our machine is only good to accurate to a quarter of an inch. So what we want to know is how far is the area off. So we want to know the potential change in the area. How would I find the potential change in the area? What would dA be? It would be the derivative times, just a few minutes ago when we had some function f of x, how did we find dy? dy was f prime of x times dx. So in this case, the change in area is going to be the derivative of area times 1/4. That's correct, times dr. Where our variable in this case is the letter r, not the letter x. All right, so dA is 2 pi r times dr. So in that case, it's 2 pi times 16 times plus or minus a quarter. 2 times 16 is 32. 32 times a quarter? 8. So our area should be exactly 256 pi square inches. But since we can be off by as much as a quarter of an inch, our area might be 8 pi too big or it might be 8 pi too small. Is that a big difference? Okay. Pretty big difference? How big? Okay, about 25 square inches. But how does that compare to how big it should be? All right, so there's a measurement for determining if this is significant or not, and this is called propagated error. I can't spell it. Propagated error and percent error. So this is what they ask you to do in part B of this problem. They ask you to find the propagated error and the percent error. To find the propagated error, it's the absolute value of dA divided by what the actual answer should be. So in this case, it's 8 pi divided by 256 pi. So it's 8 over 256. How much is 8 over 256 as a decimal? 0.03125. So Anybody want to take a guess at what the percent error would be? 3.125. So is that a big error? Your error is off by 3%. Is that significant? Yeah, it depends on your perspective. 3% can be pretty significant, right? I mean, that's the difference between an 88 and a 91 on the test. That's the difference between a B plus and an A minus. Think of it that way, it seems significant, right? So you hope that your percent error is small. 3%, that doesn't surprise me since we're off by as much as 1/4 of an inch. Okay, so while differentials, the original use of differentials isn't very practical anymore. The original use of differentials was to approximate y values of functions, which is what we did at the beginning. Not particularly useful because we have calculators that do it all so quickly and so easily now. But differentials are still used a lot in industry to compute percent error when they're building things. They need to know the percent error. They have tolerances. They have to be within a certain value. And if they're not within that certain value, they have to rethink their process. Okay? Questions on that? Let's do one more of those. Let's see if we have another good one here. How about 29? The measurement of the edge of a cube is found to be 15 inches with a possible error of 0.03 inches. Use differentials to approximate the possible propagated error in computing the volume. Use differentials to approximate the possible propagated error in computing the surface area. All right, so we have a cube. Cube of size, forgot what it said already, 15 inches per side, plus and minus 0.03 inches. So we want to find the propagated and percent error in the volume. How do you find volume of a cube? Side cubed, so it's just going to be x cubed, correct? So what should the volume should be exactly 15 cubed. How much is 15 cubed? 3,375 cubic inches. Then we find the error. The error is dV is going to be V prime times, in this case, dx, because we used x for our variable. What's V prime? 3x squared dx. So that's going to be 3 times 15 squared times dx. What's dx? Plus or minus 0.03. All right, so take 15 squared, multiply by 3, then multiply by 0.03.
Plus or minus 675.
How much?
675. Plus or minus 675.03.
675.03. And again, that would be cubic inches. All right, so our propagated error. You didn't get that?
Never mind. I added it instead of negative 303.75.
Plus or minus 303.75? Okay. Yeah, so I see you did plus 0.03 instead of times 0.03. Yep. Okay, so our propagated error would be 303.75 divided by 3375. Which is pretty small. 0.09?
The number should be plus or minus 20.25.
I got that.
The moral of the story is don't forget to bring your own calculator. All right, so now give me 20.25 divided by 3375. 0.006? Which means our error is only 0.6%. So there's our propagated error is 0.006. There's our percent error. So that's pretty good. All right, now let's repeat, except now I want to know the error in the surface area. How do you find surface area of a cube?
6 sides squared.
6 times the area of one of the sides, so 6x squared. And I'm just going to call this A for area. So again, our area should be, area at 15 should be 6 times 15 squared. 225 times 6, 850. 1350? That was only off by a little bit. 1350, all right. And then dA would be A prime times dx, which would be 12x times dx. So dA is 12 times 15 times plus or minus 0.03. Which is 5.4 plus or minus. So our answer would be the propagated error is 5.4 divided by 1350. 0.004, which means, oops, our percent error is 0.4%. So our error in finding the surface area was even smaller than our area in finding the volume. Questions on that?